Hello everyone, I'm Noah Greer, and today we'll be presenting my research plan that will be focused on multi-material metal powder bed fusion, a new and exciting branch in the field of additive manufacturing. Through this presentation, I plan to touch on what the process is, why it is significant, the current state of the art, its current challenges, and finally, I will go over my proposed plan for research that will help to support future industrial adoption. Additive manufacturing has transformed metal fabrication, enabling geometries and weight reductions that were impossible with prior processes like casting or machining. One of the most promising frontiers that is just now emerging is multi-material metal powder bed fusion. At its simplest, this is the ability to print dissimilar metals together to form functionally graded parts. My proposed research will explore how this technology can combine structural and thermal performance within a single printed part without relying on mechanical joints or welds in the material. And at the end of my research, I want to have a better understanding of how one of these promising metal mixes behaves. The motivation to take on this topic is straightforward. Many aerospace and thermal systems require materials with contradicting properties: high thermal or electrical conductivity in one region and high strength in another. With traditional manufacturing methods, these differences mean that two parts need to be made and then in some way joined. Multi-material powder bed fusion lets us transition between these properties seamlessly. For instance, in a rocket nozzle, we can integrate a copper alloy for heat transfer near the throat and a nickel or steel-based alloy for structural reliability along the outside of the throat area. The current research focuses heavily on hardware and process control. Fraunhofer, a printer and powder supplier based in Germany, is experimenting with dual hopper real-time recoding systems. Econity 3D is also offering very similar capabilities to Fraunhofer, and hybrid setups are emerging that merge powder bed fusion's precision with directed energy deposition speed, which is ideal for functionally graded transitions. Schaeffler and Arison are currently market leaders in this space with a recoder that handles up to 3 different materials. These advances help to move the technology closer to full commercial adoption. Several combinations have already shown promise. Inconel and steel blends are useful for high temperature and high stress environments, while copper or bronze and steel alloys combine their best attributes of conductivity and strength. Titanium and Inconel combinations give lightweight yet heat-resistant parts. Each pairing targets a specific balance between mechanical, thermal, and electrical properties while also opening up new possibilities for designers to take full advantage of. While progress is rapid, several barriers remain. Powder cross-contamination can cause unintended gradients. Dissimilar metals solidify in different manners, forming brittle intermetallics or high residual stresses. Thermal management during the print must also account for reflectivity and conductivity variations between the different gradations. Finally, there's little standardization for what the qualification framework should look like for these materials, which hinders industry adoption and makes designers more hesitant to use this technology for new products. Modeling and monitoring are essential for repeatability, speed, and reducing scrap material. Tools like ANSYS Additive Suite simulate the melt pool and powder interactions, and can be used to make informed decisions regarding the implementation of processes for the manufacturing of the part. In-process sensors, which would be sensors like pyrometers, cameras, and spectrometers, are there to allow real-time feedback on melt pool stability and interfacial bonding, which is critical for successful multi-material transitions in printed parts. Because of previous work I've done, of particular interest to me is the combination of copper and 316 stainless steel, and getting to understand how these two materials behave when used together in this process. My objectives are to characterize the interface between copper and 316, optimize processing parameters, and validate these results through both testing and modeling. Ultimately, I want to contribute to a data-driven system that ties process inputs together with structural and mechanical outcomes. As I mentioned earlier, I'll focus on the copper and 316 combination for its balance of conductivity and strength and its interesting applications for both thermal and electrical conductivity. I will use the additive suite tool that ANSYS offers, where I will characterize the prints and mechanical properties of my intended coupons in simulation. Then, using a dual hopper commercial laser powder bed fusion system, I'll print gradient transition coupons for several different types of mechanical testing, incorporating in-process monitoring to relate melt pool data to resulting microstructures in the metals. After fabrication, parts will undergo hot isostatic pressing and heat treatment. The hot isostatic pressing is a post-processing method that uses high heat and pressure to densify 3D printed parts and close voids within them. I use scanning electron microscopes and energy dispersive spectroscopy for coupon composition mapping. Electron backscatter diffraction and transmission electron microscopy will be used for analyzing the parts microstructures. Tensile tests following ASTM E8 and E21 will be used for determining the mechanical strength of the different prints. These ASTM standards cover both tensile testing at room temperature and elevated temperature, which are where these materials are most likely to see their most severe use cases. Hardness will be covered with micro-hardness test following ASTM E384. This standard is specifically written for hardness over short distances, which will be useful for capturing how the material changes as the mix of powders changes. To get interfacial integrity, I will use 3D X-ray computed tomography and a focused ion beam method to cross-section the printed parts for analysis. Finally, I will benchmark the residual stresses by following ASTM E837. This standard is also an area where my research can be helpful for pushing our knowledge. This ASTM standard was not written specifically for 3D printed materials, and currently, no standard exists. This research could help contribute to the creation of a residual stress testing standard for metal 3D printed materials. Altogether, these tests will provide a comprehensive understanding of how powder gradation choices shape performance, and may even help usher along the introduction of new engineering standards to help engineers make informed design decisions. The final phase integrates all data. I correlate melt pool signatures with microstructural outcomes and quantify diffusion zone thicknesses. This dataset will support predictive modeling and could potentially be fed into a machine learning algorithm to help automate process control and help guide manufacturers to the best process for their intended outcomes. For my end goal deliverables, I want to have an established process with well-defined structure and property relationships. I want to have identified the key process parameters, and finally, I want the knowledge that I gained from this experience to help push technology forward. To close, multi-material powder bed fusion is a breakthrough in additive manufacturing, enabling tailored performance within a single part. My research targets gradient control and qualification methods to overcome current barriers and bring this technology closer to industrial adoption. Thank you.